Question 3 is about this compound, which hopefully you recognise is an ester. So when you have carbonyl, oxygen, and then some kind of organic group like an alkyl group or an aryl group, that's the hallmark of an ester. And it asks you for the systematic name. So remember that this bit looks almost like propanoic acid, right? Because you've got 1, 2, 3 carbons, so that gives you the propanoate bit. And all you're doing is you're replacing that H with a connection to whatever it is. So that group, because it derives from propanoic acid, is called a propanoate group. And what's attached to it is just a 1, 2, 3, 4 carbon chain. So it's butyl propanoate is the answer to the question. And then it's talking about acid hydrolysis. So let's just be clear what the reaction is first of all before we get into what we're seeing in the gas chromatography. So remember, hydrolysis is just the reverse of esterification. So you would make that that ester, by reacting this alcohol with this carboxylic acid. Okay, so wherever that linking oxygen is in the chain, you have 2 OH groups in the original compounds, and those condense together to give you your ester. So the forward reaction is condensation, but the back reaction is hydrolysis, because the other product is water, and so by reacting with water you can drive the reaction in reverse, and that's what the hydrolysis reaction is. So you need to make sure you know that reaction. If you do it under alkaline conditions, you get the salt instead of the acid, but this is under acid conditions, so it's the exact reverse of esterification. So this is the reaction we're talking about, and therefore the 2 products of the reaction are going to be this compound, which is butan-1-ol, okay, because it's a bute-and chain, 4 carbon chain. The OH is attached to the first carbon, so it's butan-1-ol, and this is propanoic acid. So make sure you know the hydrolysis reaction, and if you remember that it's the reverse of esterification, that makes it easy. So those are going to be the 2 products, but you have to work out which one is which in the gas chromatography. Right, so this is what you can see in the gas chromatography. So this one is the sample at the beginning. Time is 0. So the sample was taken at the beginning of the reaction, and that means that you can't have any of the products yet. So all you've got is the unreacted ester. So this must be your butyl propanoate, which is your starting compound, because that's all you must have at T equals 0. So partway through the reaction, when some of this has reacted, the peak will have got smaller, and you will have got some of the products, which are these 2 peaks, because there are 2 products. There's the carboxylic acid and there's the alcohol, so 2 peaks for 2 products. And at the end of the reaction, the hydrolysis is complete, so all of the ester will have gone, and you've just got your 2 products. That's the idea. So the question was, which of these peaks is which? Because we know that one must be propanoic acid, and one must be butan-1-ol, the 2 products of the hydrolysis, but how do we know which one is which? So the key bit of evidence is that, first of all, your first thought might be, well, surely they'll have different MRs, so we can tell from the molecular ion peak. But just by a sort of quirk of fate, that one has an MR of 74, and so does propanoic acid. So unusually, just looking at the molecular ion peak doesn't help you, because those both have an MR of 74. So you have to depend on the fragmentation, and it tells you that the the one with a retention time of 15.3 minutes had a peak at 31 from formation of a fragment, whereas the other one didn't. So the question is, how can you get a peak of 31 from either of those? So if we look at the carboxylic acid first of all, if you break it there, you'll get either CH3, which is 15, or you'll get 15 away from that, which is 59. So that doesn't help you account for the 31 peak. If you break it here, then your possibilities would be you'd get 45 if you got an ion formed from the COOH fragment, or you'd get 29 if you broke it there. If you broke it here, you just take 17 away in the form of OH, and if you take 17 away from that, you get 57. So you could account for any fragments of those sizes, but none of those is 31. So that one has no M over Z equals 31 fragment. So that suggests that it's going to be the one with retention time of 16.6 minutes, because it tells you that that compound with the 16.6 minute retention time didn't have a peak at 31. But that argument only makes sense if you can show that the other one does have a fragment of 31. And if you break it here, you can see that you can get CH2OH, and CH2OH has 14 for the CH2 plus 17 for the OH, 31 fits there. And that's the key thing. So if you generated a molecular ion from butan-1-ol, it could break at this position and give you a fragment which would be CH2OH plus. Okay, just by breaking it at that position, CH2OH would break off. And if that one has the positive charge, it would be CH2OH plus, and then you detect it, which gives an M over Z of 31. So that fits then. So that implies that butan-1-ol has a retention time of 15.3 minutes. Okay, so that's just about making use of what you know about gas chromatography in tandem with mass spectrometry, because that combination commonly goes together. So when you get questions about gas chromatography, they're quite likely to be linked to analysing mass spectra like that. And if you're lucky, you can just use the molecular ion peak to distinguish between possibilities, but sometimes, as that example shows, you can't. And so in that case you have to think about the fragment. But it's just remembering only single bonds can break in our analysis of fragments. So if you just go through and look at the possibilities, you can work out whether you can account for a particular mass. So that gave you your answer as to which one was which. And then it said, okay, comparing the retention times. So we've now, if we just mark those on here, this one is the 15 is the butan-1-ol, and this one is the propanoic acid. And it asked us to use the differences in retention time to suggest what you can about the polarity of the column. So to answer that, you need to remember how gas chromatography works, and you need to be ready to do questions like this which depend on you just having a simple model for what happens in gas chromatography. So if you imagine that you just have this long column, the idea is that the gas goes in at one end, and you have a detector here, and you inject your sample there. And because it's hot, the sample vaporizes and the molecules will get carried along in the gas. But lining the column, you have this liquid stationary phase. And it's stationary, meaning it's not moving. So the gas is moving, but the liquid is not. The liquid is fixed on the walls of the vessel. So what will happen is the molecules of the sample get carried along in the gas, but they will have some tendency to dissolve in the liquid, just reversibly. So if a molecule happens to dissolve, it will dissolve in the liquid, and because the liquid isn't flowing, it will be stuck there until it vaporizes again. Then it will get back into the gas and keep moving, but then it might dissolve again and stop for a while before it vaporizes and keeps going. So the bottom line is that the more soluble a substance is in the stationary phase, the more time it will spend in the liquid. You know, common sense tells you that. The more soluble it is in the stationary phase, the longer it spends stuck in the stationary liquid rather than being carried along in the gas. So therefore, higher solubility in the stationary phase means a longer retention time. Okay, so you need to understand the principle of gas chromatography at that level, and they will very commonly ask you to make that statement. But here it asks you to do more than just that, but actually to apply that idea and say, well, what that means in terms of these data is this one has the shortest retention time and therefore is the least soluble, just applying that principle. So what would make this less soluble than these? And the key is hydrogen bonding. Okay, this has no OH groups, so it can't form hydrogen bonds, or at least it can't form hydrogen bonds using any of its hydrogens, whereas these ones can. So these ones are likely to be more soluble because they're able to form hydrogen bonds to the stationary phase. So what kind of stationary phase can form hydrogen bonds? A polar one or a non-polar one? Well, obviously the answer is polar. So that's what you were meant to deduce, that because this ester has the shortest retention time, this rule tells you shortest retention time corresponds to lowest solubility. And then you just compare what would make an ester less soluble than these compounds, and you just look at those and see hydrogen bond, that's going to massively increase the solubility if the solvent is polar, so it itself can become involved in hydrogen bonds, whereas this can't form hydrogen bonds, so it's less polar and it's going to be less good. So that was the basis for that one, so the correct answer was polar. It then gives you the rate equation, which is that. So it's first order with respect to compound B, which is this ester here. And it asks you, just using these data, to estimate the rate constant K in this rate equation. So you've got to think, well, what method do I know that can give me an estimate of the rate constant for a first order reaction? And the answer is half-lives. So what you need to remember is that K is equal to log 2 over the half-life for a first order reaction. Okay, so you have to know that that's true, and you have to think of using it here, because you can see how you can estimate the half-life from these data. Because at this point, you can see that the size of the product peaks is the same as the size of the reactant peak. That means that half of the reactant has been used up and turned into product, right? Because if you've got, a total of, say, 1 mole, after a half-life, you'll only have half a mole left, and you'll have formed half a mole of each product, and that's where you're at here. So that means that that time point, which is 10 minutes, is equal to the half-life, because that's the point at which half the reactant has been used up and converted into product, and that's unequivocally true from the pattern that you see there. So you then just have to plug the numbers into there. So you get that K is equal to the natural log of 2 over 10, which is 0.0693. And the units, well, it gave you those in the question, but for a first order reaction you'd normally expect second to the minus 1, but because we're working in minutes, it's minutes to the minus 1. Okay, so again, you've just got to have that ability to sort of recognise that yes, you normally think of this as an organic method, but it gives you these quantitative data. You need to know that the peak areas are proportional to the amount of substance, and therefore if half of the reactant has been used up, the time taken here is equal to the half-life, and that gives you a value for K if it's a first order reaction, which is what it told you it was. Okay, so then it asks for this graph of rate as a function of concentration of B, and we've got the rate equation, and that equation tells you the form of the graph, right? Because this relates rate to concentration, and you can see that's just a straight line graph, because it's like y equals mx, no constant, which means it goes through the origin, so it's just y equals mx, so it's that straight line graph like that. So finally in question 3 then we get this question about the temperature dependence. So remember, if it's about the temperature dependence of K, we're talking about the Arrhenius equation, and the Arrhenius equation is on your data sheet. And in particular, if it's talking about this graph of log K versus 1 over T, which is what most Arrhenius questions depend on, then the form of the equation you want is this one, that log K equals minus EA over RT plus natural log of A. So that's one of the forms that's given to you on your data sheet. And if you just slightly rearrange that to say log K is equal to minus EA over R times 1 over T plus natural log of A. So all I've done is taken the T from the bottom line there and taken it out as 1 over T. Then you can see that that's an equation of the form y equals mx plus c. Okay, where m is minus EA over R, x is 1 over T, c is natural log of A, and y is natural log of K. And that, of course, is a straight line equation. So what that tells you is that if you plot y against x, in other words log K against 1 over T, you'll get a straight line. And what you hope to remember is that m is the gradient, and therefore the gradient of this graph will be minus EA over R, and that's the key to the question. So when you get a graph like this, it looks like that it has a negative gradient because EA and R are both positive numbers, so minus EA over R will be a negative number. So that's what Arrhenius plots always look like, and or in a normal question you would get to measure the gradient off the graph, but here it just told you the value is equal to minus 9620 Kelvin. The units don't really matter, but that's what they work out to be. So you can see that that's what the gradient equals. So if we multiply the gradient times minus R, so just rearranging this expression, if we multiply the gradient by minus R, we'll get the activation energy. And that's all you needed to do. So if this is something that you don't particularly like and you have to sort of work hard to see, then it's worth memorizing this relationship. Because if you get Arrhenius questions, most likely it's going to be based on a graph, and if you know that the gradient is equal to minus EA over R, you can just do the calculation, even if you're a bit shaky, seeing where it comes from in the equation. So that's up to you, but I think that's something that's worth knowing, because it just makes your life easier when you come to an exam. So anyway, we can just plug the numbers in. So we've got the gradient is minus 9620, and R is on your data sheet. Remember, R is the gas constant, which is 8.314 joules per Kelvin per mole. And if you multiply those together, you get, because we're multiplying minus 9620 by minus R by minus 8.314, we've got a minus times a minus, which equals a plus. So it comes to plus 80,000. And that will be joules per mole. And you know it's going to be joules because when you look up R on your data sheet, it tells you that R is equal to 8.314 joules per Kelvin per mole. And because that number is in joules, when you compute something from it, it will be in joules. But the question asked for it in kilojoules per mole, which of course is what chemists normally use for energy terms. So you have to divide by 1,000 to get the kilojoules per mole. So that's plus 80.0 kilojoules per mole is the activation energy.